Here we have a chart kind of to illustrate what that paragraph was telling us on the last page. I'm actually going to start in the middle. So for each of these, we have a graph of a quadratic function. So our expression on the first one is 3x squared plus 6x minus 2. Noticing from the graph, this crosses in two spots. Sorry, that's a little bit off. And then this one below it, negative 2x squared minus 6x, also crosses in two spots. The lead coefficient is negative, so the graph opens down. In both of those cases, I'm just going to add a plus 0 here so we can see the c value. B squared is larger than 4ac. So for example here, if I do b squared, that's 36. And 4ac is 4 times 3 times negative 2. So 36 is definitely bigger than negative 24. Another way we can say this, if we calculated b squared minus 4ac, so 36 minus negative 24, that's greater than 0. So when I put that answer, which in this case is 60 in a radical, I would get plus or minus square root of 60. That's going to give me two real answers. Looking at the next case, if I look at this quadratic, right, it has no real roots. And the same thing with this one just has that negative lead coefficient, so it opens down. When I examine these expressions, which are what we're graphing, here, if I do b squared, for example here, b squared is 9, and 4ac is 4 times 1 times 7, which is 28. So if I do 9 minus 28, that's less than 0. So that number, negative 19 in this case, would be in the radical, creating those imaginary solutions, which agrees with what that graph looks like. At the bottom of the page, I didn't do this one for the first one, but the same thing would be true. I am going to do this one, though. So b squared is 4 squared, which is 16. And 4ac would be negative 4 times negative 1 times negative 6, which is 24. 16 minus 24, that's going to be a negative number. So you can always use a subtraction method. I find when I think about b squared versus 4ac, finding those two values, I can quickly look at a quadratic and know what type of roots it's going to have. Our last situation is when the two are equal. So it doesn't cross twice. It doesn't not cross at all. It crosses in one spot. So here, if I do b squared, and this one's pretty similar to the one I did on the other page, so I'm not going to use that as an example. I'm going to look at this one down here. B squared here, 4 squared is 16. And 4ac is also 16. So if I do 16 minus 16, that equals 0. And if we think about the whole quadratic formula, that would give us plus or minus the square root of 0, right, where the b squared minus 4ac goes. This is going to give me the same solution, right? Not two different numbers. If I add or subtract 0, I'll get the same thing. So looking down at the bottom of the page, we'll start to think about that. I am going to, on the first set, just talk about actual b squared minus 4ac to decide whether each quadratic has real or imaginary roots, and then indicate when the graph has a double root. So that's when we get that 0 for the discriminant. So if I'm just looking at this equation, if I do b squared minus 4ac, the discriminant, I would get negative 3 squared minus 4 times 1 times negative 10. Now, without actually finishing this, I can already see it's going to be positive because I have a negative times a negative. So this is going to be 9 plus 40, which is 49. That's a positive number, right? So we are going to have real roots. My next one, for b squared minus 4ac, I have 6 squared minus 4 times 1 times 10. That gives me a negative 4, so that's complex or imaginary roots. Sometimes complex and imaginary are interchangeable. When we use those words, technically imaginary numbers are just talking about that there's an I in them, whereas complex numbers have the real and imaginary parts. So technically this is complex roots, but sometimes we refer to them as imaginary as well. My last one, 3 squared minus 4 times negative 2 times 4. You can already see that's going to be positive. So this is 9 plus 32 is 41. So we have real roots. On the next one, I'm going to start to think about these problems in terms of just comparing those two. So this is the other way. So if I do b squared, that would be 144. 4ac would be 4 times 1 times 36, which is actually also 144. So if I subtracted those two, since they're equal, I would get that my discriminant is 0. When it's 0, that means we have real roots, but that's that double root where the two roots are in the same location or it's tangent to the x-axis. And I didn't mean to make that plural, just a double root. My next one, if I do negative 13 squared, right, that's going to give me 169. And over here, 4 times 3 times 4 is 48. So we can see if we subtracted those two, right, that's going to give me a positive number. So that is real roots. My next one, we have for b squared, negative 4 squared is 16, and 4ac is 4 times negative 4 times negative 5. So that's 16 times 5, right, because those negatives will cancel. That's 80, right? So this, if I subtracted those two, even without finding it, that idea is that you can think about that in your head. Because that number is going to be negative, this one has, and I'm going to write complex this time just to show that either way works. So I tried, the idea of the technical traditional way to do this is to find b squared minus 4ac, like we did on this top set of problems. Okay. But the way I did D through F, that's something I can actually do in my head. And the reason I do that is because that helps me think if I see a quadratic, if it has complex solutions, there's going to be i's in there. I definitely have to use the quadratic formula, and there's no way I'm factoring. So these are all decisions that you can make from just looking at a quadratic. For example, when I look at this, okay, in my head, I do 13 squared, right? That's 169. And I know, even if I don't know exactly what 4 times 4 times 3 is, I know that's smaller, so I know I'm going to have real roots. So unless it's super close, you might actually have to calculate it. You can actually look at a lot of them and just make a decision at a quick glance.